Good morning to all. I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the Davisson and Germer's experiment. So, in this topic, we are going to cover the introduction part and theory of Davisson and Germer's experiment, and then experimental setup, explanation, and we'll see the observations. So, these are all the topics we are going to cover in this session. Okay, first of all, we shall move to the introduction, Davisson and Germer's experiment. So, in 1927, the two American physicists, Davisson and Germer, was given the first experimental evidence for the matter wave. So, matter wave is nothing but dual nature of a particle. So, wave nature and also particle nature. So, the explanation, that is the wavelength of the matter wave, also we have been discussed in the previous sessions, and also we derived an expression, that is lambda is equals to h by mv, which is given by the de Broglie. So here in 1927, the two American physicists, Davisson and Germer, was given the first experimental evidence for the matter waves. This is the supportive to that matter waves. So the apparatus consists of an electron gun, where the electrons are produced. So in this apparatus, it consists of an electron gun G, where the electrons are produced. So from the electron gun, electrons are produced. So when the filament of electron gun is heated, dull red electrons are emitted due to thermionic emissions. Due to the thermionic emissions, the filament will be heated and then it produces the red color electrons. So these electrons are accelerated in the electric field of potential difference and are collimated by suitable slates to obtain a fine beam. So which were emitted by the electron gun due to the thermionic emissions from the electron gun. So these were accelerated in the electric field, which have certain potential difference, and then it has been collimated by suitable slates to obtain a fine beam of electrons. So then the collimated beam of electrons are directed to fall on a large single crystal of nickel. So here the crystal we used is single crystal, which is nickel. Okay, so the nickel crystal also called as a target crystal, which we are going to make the electrons to fall on that crystal. So this nickel crystal is a target crystal. So the fine beam of electrons was directed to collimated to fall on a large single crystal of nickel. So after hitting the target, the electrons scatters in all directions. So when the electrons hits the target nickel crystal, then the electrons scatters in different directions. So this can be detected by an electron detector. The scattered electrons can be detected by an electron detector called as Faraday cylinder, which is connected to the galvanometer. So this can be the scattered electrons can be detected by an electron detector. This detector also connected to the galvanometer. So this electron detector or Faraday cylinder can move on all circular graduated scales between 29 to 90 to receive the scattered electrons. So to receive the scattered electrons which are scattered in all the directions, so that here there is an attachment of a Faraday cylinder, so that can be moved in all circular graduated scales. Okay, so it can be received 29 to 90 to receive the scattered electrons. So here the experimental verification of Davisson and Germer for the matter waves. So here in this diagram, a heated filament of electrons which are produced the electrons which are produced the electrons. So here there is a filament. So when the filament is heated, when the filament is heated, it produces dull red electrons. It produces dull red color electrons. So it is producing electrons. So then the electrons are accelerated by electrodes and directed at a crystal. So here we are giving some potential difference. So we are giving, it is connected to the voltage. So certain voltage, certain potential difference, what happens, the electrons are accelerated with sufficient velocity and are passed towards the electrodes, so that we'll get fine beam of electrons. We'll get fine beam of electrons. So these electrons falls on the nickel crystal. This is target crystal. So electron strike a nickel crystal. So it is a target crystal. So it is a target crystal. So after hitting the electrons, after hitting the target crystal, so the electrons scatters in all directions. The electron scatters in all directions. So different directions they are scattered. So these scattered electrons can be detected by the electron detector or Faraday cylinder. So the detector can be moved to detect scattered electrons at any angle theta. At any angle theta. So this is the electron detector. And it is also connected to a galvanometer. Okay. So first thing is here, this is an electron gun. So this electron gun consists of a filament. When the filament is heated, it produces dull red electrons. So this velocity is not, these electrons velocity is not sufficient to hit the target crystal, so that we connect it to the voltage source, so that by so that at a sufficient voltage the electrons are accelerated. So these accelerated electrons are passed towards the electrodes, so we'll get a fine beam of electrons. Fine beam of electrons. So these electrons then falls on the nickel crystal, which is a target crystal. So after hitting target crystal, the electrons can be scattered in all directions. So that scattered electrons can be detected by the electron detector, and then which is connected to the galvanometer also. So the electrons which are scattered in different directions can be detected by the electron detector. Electron detector. So the complete apparatus will be in the vacuum chamber. So here the high tension battery is there, and here the low tension battery. This is the filament. So the filament, when it is heated, fine beam of electrons are coming. So that we are getting the fine beam of electrons, so which is called as a instant beam. Instant beam. So this incident B is hitting the target crystal, nickel crystal, so it is scattered with some angle theta. So the diffracted beam is collected by the detector, electron detector, which is movable in all directions, and it can be collected the scattered electrons. First of all, the accelerating potential V is given at a low value and the crystal is set at any orbital as so that first of all we are giving accelerating potential some V at a low value. So low value of accelerating potential we are going to set, and so that the crystal is set at any orbital azimuth theta. So now the Faraday cylinder is moved to various positions on the scales and galvanometer current is measured for each position. So when we set the accelerating potential to a low value of V, so the scattered electrons will be scattered with some angle theta. So the scattered electrons can be collected by the electron detector. So Faraday cylinder is moved to various positions on the scales and the galvanometer is measured for each position of the scattered electrons after hitting the target crystal. So then a graph is plotted between galvanometer current against angle theta between incident beam and entering the cylinder. Okay, so here we are plotting the graph. So a plot is drawn between galvanometer current against angle theta. So this angle theta is in between instant B and B entering the cylinder. That is this one and this one. Okay. So scattering angle. So galvanometer current against scattering angle theta. So that scattering angle between instant beam and then the scattered beam which is entering into the cylinder. So the observations were repeated for different accelerating potentials. So initially we started at a low value of potential, accelerating potential V. Then we are going to increase gradually. So as the potential accelerating potential is increasing, so the angles, the scattering angles also be different. So the observations are repeated for different acceleration potentials. So, uh, when we say that accelerating potential and then scattered electrons, so at the low value of 44 volts, at the low value of accelerating potential 44 volts, so the accelerating electrons or the electrons, the scattered electrons are hits in this way. So we can see here a bump here, we can see the small bump here. So when we increase 48 volts of accelerating potential, so the beam is somewhat high than comparing to the low accelerating potentials. At 54 volts, we can see large bump. You can see the large bump. So the angle is of 50 degrees. The angle is at 50 degrees. Then it goes on increasing the accelerating potential. Then the bump is reduced. The bump is reduced. So we can observe that bump is begin to appear in the curve at 44 volts of accelerating potential. So with increasing potential, the bump moves upwards. The bump moves upwards. The bump becomes most prominent in the curve of for 54 volts at theta is equals to 50 degrees. So here in all the accelerating potentials, we can observe at 54 volts, the bump is large. The bump is large, and the curve 54 volts, the bump is very large comparing to different accelerating potentials. And the theta is 50 degrees. So with increasing potential, the bump moves upwards. The bump moves upwards. Increasing potential, the bump moves upwards like this. The bump becomes most prominent in the current for 54 volts at theta is equals to 50 degrees scattering angle. So at higher potential, the bump gradually disappears. The higher potential, so here the 44 volts it started and goes on increasing. At 54 volts, it becomes larger curve at theta is equals to, where we get theta is equals to 50 degrees of scattering angle. Then at 64 volts, the bump is reduced. Then after at 68 volts, so we can observe very little bump here. So that the bump becomes most prominent in the curve for 54 volts and theta is equals to 50 degrees. So at high potential, what happening? The bump gradually decreases. The bump gradually disappears. According to the de Broglie, the wavelength associated with electron accelerated through potential V is given by lambda is equals to 12.26 divided by root V. So which we got this from lambda is equals to h by mv, and taking as and when taking the kinetic energy and potential difference, we'll derive the expression of de Broglie wavelength, which is accelerated through some potential. So that formula is lambda is equals to 12.26 divided by root 2 V angstroms. Okay, so hence this lambda is for the electron which is accelerated through a potential V. So for that, the de Broglie wavelength lambda is equals to 12.26 divided by root V angstroms. So hence the wavelength associated with an electron, accelerated electron through 54 volts is lambda is equals to 12.26 divided by root 54. That is equals to 1.67 angstroms. 1.67 angstroms. So we are substituting capital V. So what is the capital V? So 54 volts. So we are getting large bump at 54 volts. So we are taking the wavelength of the particle which is associated with a wave. Lambda is equals to 12.26 divided by root 54. So the calculated value is equals to 1.67 angstroms. So from X-ray analysis, it is known that a nickel crystal acts as a plane diffraction. Nickel crystal acts as a plane diffraction grating with the space T is equals to 0.91 angstroms. So when we take nickel crystal, so this nickel crystal acts as a plane diffraction grating. So the space where is the space is D. So that D is equals to 0.91 angstroms. Wherever we can take the interplanar spacing between the two plates. D is equals to 0.91 angstroms for the nickel crystal. So from X-ray analysis, we know that nickel crystal acts as a plane diffraction grating. So which have the interplanar spacing D is equals to 0.91 angstroms. So according to experiment, we have a diffracted beam. We have diffracted beam angle theta is equals to 50 degrees. Theta is equals to 50 degrees. So that the corresponding angle of incident relative to the family of Bragg's plane, theta is equals to 180 minus 50 divided by 2. So the corresponding angle of incidence relative to the family of Bragg's plane, theta is equals to, theta dash is equals to 150 minus 50, 180 minus 50 divided by 2. So we are getting 65 degrees. So using Bragg's equation, so lambda is equals to 2d sine theta. So from the Bragg's equation, lambda is equals to 2d sine theta. That is, n lambda is equals to Bragg's law is n lambda is equals to 2d sine theta. As we are taking order of the plane is n is equals to 1. So 1 into lambda is equals to 2d sine theta. So that lambda is equals to 2d sine theta. And so that here we are taking lambda is equals to 2d sine theta. So it is equals to 2 into the interplanar spacing t is equals to 0.91 into sine 65 angstroms. Sine 65 angstroms. So here, what is this 50? So 50 is scattering angle theta. So scattering angle theta. Theta is equals to 50 degrees. 50 degrees. So that 180 minus. So maybe the instant field falls, hits the target nuclear, the target crystal. So it scatters with some angle theta. Suppose we draw a normal to this. So here to here 180 degrees. So 180 minus the scattering angle is 50. So 180 minus 50 divided by 2. So we are getting 65 degrees. So theta is equals to 65 degrees. So lambda is equals to 2 into 0.91 into sine 65 degrees. So that we'll get the value lambda. So this is a good agreement with the wavelength which is computed from the de Broglie hypothesis, and hence it is confirmed the de Broglie concept of matter waves. So here initially we have calculated the wavelength is calculated through the de Broglie wavelength associated with electrons accelerating through a potential V. Lambda is equals to 12.26. Lambda is equals to 12.26 divided by root 2. So accelerating potential is 54. So from this we'll get lambda is equals to 1.67 angstroms. Where in the case of from the Bragg's law, so lambda is equals to 2d sine theta. Lambda is equals to 2d sine theta. So it is equals to 2 into 0.91 into sine 65. So what's the value we get here? So it is equals to point into sine 65 angstroms. Okay. So it is equals to sine 65 1.6494. So get 1.65 angstroms. So as here the value of sine 65 is equals to 0.9063. Okay, so 1.82 into 0.9063. At the value lambda is equal to 1.6494. So from the de Broglie wavelength, lambda is equals to 1.67, where in the case of lambda is equals to 2d sine theta, that is n lambda. From the equation, n lambda is equals to 2d sine theta, where n is the order of the plane. So order of the plane means 1. So that we have to take here this diagram, the first plane, this plane. So according to this formula, n lambda is equals to 2d sine theta. This is the nickel crystal lattice plane. So here first plane, second plane, like this, because it is a plane diffraction. So this is incident beam of electron. So when it hits the target nucleus for the first plane, it scatters with some angle, so 50 degrees. So when we draw the normal, so that here what happens, here to here 180 degrees, 180 minus this 180 minus 50 to centimeter angle. So 180 minus 50 divided by 2. So having 65 degrees. So that lambda, when substituting sine 65, we get lambda is equals to 1.6494. So it is lambda nearly 1.65 angstroms. So from the Bragg's law, the calculated wavelength of an accelerating electron lambda is equals to 1.65 angstroms, where in the case of de Broglie wavelength lambda is equals to 1.67 angstroms. So that it is a good agreement with the wavelength computed from de Broglie hypothesis, and it confirms the de Broglie concept of matter waves. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.